王处，您稍微稍等一下。王处能听到吗？
听见，我听得很清楚。
稍微稍等一下，我们那个学员现在上线，正在陆续上线，你们等个1-2分钟吧。
没问题。这个背景好做吗？这个背景，这个 Zoom 里这个背景，我到现在没换成。
我把这两个加。因为它是这样的，就是如果说是你就是这样加入会议的话，它是这个王处。它那个背景是这样的，我们了解了一下，就是如果是你普通的这样参入会议的话呢，它是只能用它内置的几个背景，就是那种模糊的呀，或者是他们自己自带的一些背景。然后的话，如果说是你想要换你自己的那个背景的话，那它就是需要你去专门购买一下他们的账户，就是购买一个账号，这样子。
对，我之前开 Zoom 的会议也都没成功过，所以就算了。我这里只有它普通的下载版本。
我本来下播的时候想问您是不是要用，我们可以去找一下，看看能不能找到账户啊。就是它这个账户是可以购买的，但是后来可能您忙没有看到，本来是想问问您是不是需要您自己的。那王处，我们现在开始，然后我先给您介绍一下，然后你就再直接开始。
好。
Okay, dear participants, so let's start with our second session. And in this session, we are very glad to invite Mr. Wang Xiaobo, who is the Deputy Director of Science and Technology Development Department of China Energy Construction Group. And Mr. Wang has mainly been engaging in the research on new energy and digital technology. And he is a strategic advisory expert of Asian Development Bank and Huawei Digital Power Technologies Corporation Limited. And he also took part in many major planning and research projects, such as the 15th five-year plan for energy technology innovation issued by National Energy and Administration, Carbon Neutral Technology Development Plan issued by Ministry of Science and Technology, etc. And today we would like to talk about the wind power. So let's welcome. So Mr. Wang, please.
Okay. Thanks for the invitation. The subject of today's presentation is introduction to the wind power. So wind power and the solar power is currently playing the most important role in the energy transition in the world. So today's focus is about the wind power. I will divide this presentation into 3 parts. The first part, part 1, is the general principle of the wind power generation from the turbine and any other element. The part 2 is about the onshore and offshore wind power industry presentation. And the part 3, if we have the related time, is about the innovation trend of the wind industry. Okay, let's go to the part 1. It's about general principle and the fundamental of the wind power industry. The wind power in history, it's a very simple but long story. As we can see, the rise of the wind powered electricity. The origin is from 2 countries, Denmark and the US. As we can see, in the latest of the 1940, the rural electrification in US and Europe, these two decline in the WECS use. I will use the indicator, okay? You can see in the right indicator. So we use the abbreviation for many times. The wind electricity conversion system, WECS, the wind electricity conversion system, WECS. So it's a very long story, but simple. The brief history is about the modern industry, the current situation. We can see the key attributes of this period. We can see the scale increase. We are getting the larger turbine. The commercialization, we are getting the business model. So we have a very popular business model for the wind power generation and integration. And the competitiveness. We can compete with the solar, even with the coal-fired power plant. And the grid integration is crucial and the most important element for the renewable energy. If the renewable energy cannot be connected to the grid, if the renewable energy cannot get a very good grid integration, it will lose its competitiveness. Okay. And we can see the catalyst for progress, the OPEC crisis, the oil crisis. Because we have the oil crisis, we have the OPEC crisis, the renewable energy for two reasons. We get the orientation for the renewable for two reasons. One is the economics. We want the renewable cheaper. And the secondly, is the energy independence. So currently we get a new era. Why? As the war between Russia and Ukraine. So the energy independence has another level in its importance. So we can see the turbine standardization. We get the turbine bigger and bigger, and we can getting the turbine similar and similar. Different manufacturer, different supplier offers very similar turbine. So the wind physics basics. So wind is atmosphere's air in motion. So why we have this moving air? So energy source, solar radiation differentially absorbed by Earth's surface, converted through convected process due to temperature difference to the air motion. So some people consider that the wind power is a secondary energy to the solar radiation or to the solar power. So a lot of people say that the primary energy is the solar. All the others are the secondary energy. The fossil fuel is from the solar from quite a long time ago. And the wind power is also from the solar radiation, but in different area, in different temperature. So we can see that the wind is caused by the differentially allocated solar. It's a very interesting atmosphere. And spatial scalar, this is due to the rotation of the Earth. It's very obvious. And the wind type, we can have a very different types of the wind. We have the jet stream, the trade wind, and the polar jet. All of these are equivalently converted into electricity by the turbine. The wind resource variability and uncertainty is also to the solar. From day to day, week to week, month to month, and year to year. If we have a year to year calculation or estimation of the wind power, we may have quite a similar number between this year or next year. But the day to day or the week to week, we have the variability and uncertainty, that's for sure. There's also the challenge for the wind power integration. If we only have 5% or 10% penetration of the wind power in the grid, this problem is not so serious. But if we are getting 20%, 30% of the renewable, especially like wind, integration of in the grid, this uncertainty, this variability is becoming a huge issue for the safety operation of the grid. It will be cause the huge damage and blackout. And the wind profile structure. So this will conducted or deduced to the turbine type and manufacturing. It's the fundamental of these things. Climate and the weather models. So we need to establish the global climate model, especially as the numeric weather prediction models and the computational fluid dynamics. In this case, we want to have the estimation of the future wind power generation potential. Secondly, we need to know what type of turbine will be the best fit for the circumstance and the climate or the weather model. The wind power fundamental, we get the fundamental of the wind generation, but how we can get the wind from the wind to the power, that's the key issue. The fundamental equation of the wind power. So this is very important equation. So in this case, the wind speed, the speed of order, we can see the speed of air or the velocity is the most important parameter in this case. Sometimes, why we have the offshore wind, the construction and the turbine of the offshore wind power plant, it's much more expensive than the onshore wind power plant. Why we can still get the economics of the offshore wind? Because in the offshore wind power plant, we have the very, very good, even much better speed of air, the velocity of. So in this case, we can see that. So the wind power depends on the amount of air, the volume, the speed of air, the velocity, and the mass of air density. The mass of air of density varies very little from different places, very little. So in this case, the kinetics energy, the mass and the velocity and the power. So in this case, we can see that 3 times. This is the 3 times the cube of velocity. So when we have the selection of the wind power plant location, the speed of air or the velocity is the most important parameter. The wind power density, the wind power density per unit area. So we want for detected for a specific place, we want to install more turbine of the wind power generation. In this case, we can get more energy from same place. So in this case, we can have a different classification or allocation of the space. Due to the US, the National Renewable Energy Laboratory, they have a classification of the different places of the wind resources in the US. In the later slide, we can see the situation of China. We can see that the different in 7 different levels: the poor, marginal, fair, good, excellent, outstanding, and suitable. And if we need to say, just see the wind speed as the most important element. As you can see, if we have a wind speed larger than the 9.5 meters per second. It's a super bowl. Generally, all the offshore wind power plants have the wind speed in the super bowl allocation. And that's why we encourage people to construct the offshore wind plant for several reasons. In the later slides, we can see that. Firstly, it has the super bowl speed of wind. Secondly, it does not use the land. So we go to the ocean. It saves the land allocation, sand usage. And we can see the Weibull distribution of the wind speed. So the main speed, because in the day-to-day, we don't have the same wind speed in the same location. So sometimes we need to get to the average number. And we can see the average wind power density. How can we calculate that? Especially, we can also introduce the energy pattern factor to have a better understanding or better estimate the wind condition of this place. Okay, another thing after analyzing the wind parameter of itself, we can go to the efficiency in extracting wind power. We have the CP, the power coefficient. It is the ratio of the power extracted by the turbine to the total power contained in the wind resources. No matter we get what kind of turbine, there will be loss. We cannot convert it 100% from the wind to the power generation. That's impossible. There will be always loss. So we can see that the best limit is a maximum possible CP. So as we can see, 59 efficiency is the best a conventional wind turbine can do in extracting power from the wind. That's a physical limitation. We cannot go beyond than that. Generally, we can never get this to getting to this number. Never. So give is the upper limit of the extracting. So if you can see a report or data that will have a conversion limits beyond that 60%, that's impossible. That's impossible. Okay, let's go to the power production and the wind variability. The capacity factor. This is a capacity factor compared to the fossil fuel power plant. Because in the fossil fuel power plant, we can regulate the output of the plant. So we can operate it like continuously, always meet our need. But the wind, as you can see, the wind frequency distribution, it cannot always at the wind speed we need. If it's lower than the wind speed we need, the output will be lower than the power we expected. But in this case, we need a factor like a capacity factor to know that in which time it's operating in the capacity factor we need. Okay, so the capacity factor means that the fraction of the year the turbine generator is operating at the rated power. It can not always operating at the rated power. It's very different from the fossil fuel power plant, coal-fired, gas-fired, both. We can always want the fossil fuel power plant to operate at its rated power. So we can see that the annual energy generation is the rated power, multiple year, and CF. So in this case, we can see that the CF is based on both the characteristics of turbine and the site. because in the start we have the specific wind speed, integrating the power curve with the wind resource variability. We can see the wind resource. So we can see, generally, we can see the capacity factor of wind or solar. So in the capacity factor, it's the calculation method is similar between solar and wind. So we always can see a capacity factor of wind or solar. It's much lower than a fossil fuel power plant. In this diagram, we can see that the wind speed variation. For example, for a dedicated turbine, we have a wind speed lower than 5 meters per second. So it's operated under the rated power. So it cannot be calculated in the capacity factor. Now, let's go to the wind power technology introduction. Turbine. Turbine is always one of the most important equipment of the wind power. The turbine is from Latino, tubo, or from français, turbine. So the vortex. The turbine is the rotary engine, converting flow motion to the shaft rotation from the rotating airfoils, the wind flow. So it's in this case, as you can see, the wind flow provides the lift force, also the drag force in the turbine to let the turbine rotate as quickly as possible. Let's see the lift and the drag forces. We can see the angle of attack and the pitch angle. This is very important in the turbine design. A lot of calculation has been done to give the best ratio between these two diameters, as you can see. In the turbine in the power generation, almost all electrical power on Earth is produced with a turbine of some type, except for solar. Solar is very unique. There is no rotation machines. The nuclear, the coal-fired power plant, the gas-fired power plant, the wind power plant all have a turbine. But in the solar, there is no. There is output directly of a DC like 24 voltage. So we have an inverter to convert it to a different levels of voltage. So solar is unique. So the rise of the solar industry caused in some level a crisis of the mechanical industry. As we can see, the car industry, the vehicle industry, the power industry always have always based on the mechanical, but solar has break the rule. Okay, let's go back to the wind power. Okay, let's compare that. It's very important, very interesting to have this understanding. I know that quite a lot of East or South Asia country always operate the gas-fired or the coal-fired power plant as a base load in their grid. So let's make a little bit comparison. Traditional boiler that is coal-fired. We have a combustion turbo, external, internal, both. But in this case, we can call turbine type steam turbine. The boiler, traditional boiler. The IGCC both have a gas turbine and steam type because it's a combined cycle. It has two cycles. Like the combined cycle of gas turbine. Combustion type turbine and gas turbine. They always have a shaft and the electrical conversion like a generator. Nuclear also, nuclear. The conventional island of the nuclear power plant is similar to the steam cycle of the coal-fired power plant. Okay, and then we go to also the hydropower, wind power, and any other. Solar thermal also have a turbine. So we can see that only the fuel cell from hydrogen, hydrogen fuel cell, and PV, the photovoltaics, have a direct primary power conversion with the inverter at the downstream. It's very interesting. And also fuel cell and PV has immense, huge potential in the future. So during the development of the turbine history, there have been quite a lot of different type of the turbine. We can have the horizontal, the vertical, the upwind facing, the downwind facing, and the lift force driven, drag force driven. We have plenty different times. But as long as go, all the industry concentrate their R&D energy or R&D resources into the unique platform, As we can see, the wind turbine types, the vertical axis, we nominate it as the VAWT, and the horizontal axis. They are not very conventional, and they cannot develop as a very large wind power plants due to their physical limitation. And the rotor solidity, the blade platform is the shape of the flat wise blade surface. This is the mainstream of the wind power generation plant. We can see that the solidity is the ratio of the total rotor platform area to the total swept area. We can see the solidity. This is the minor A, and this is R, and the big A. We can have this calculation. And the tip speed ratio. This tip speed ratio means with the speed at this point. We do not need the wind to rotate very quickly, because we have a speed transmission inside of the generator, which means even the turbine rotates at a very low speed, but we can have a transmission downstream to transmit it into a very high speed in order to have a better generator output. So we can see that the tip speed ratio is a ratio of the speed of the rotating blade tip at this point to speed of a free stream wind. But if we have a better ratio, which means we have a better conversion of the wind energy. In this case, we needed to have a better design of the blade of the turbine of itself. Yeah. And for the rotor design, we can see that the power coefficient, the CP, and the torque coefficient, all these parameters, that's the core parameter we take into consideration during the turbine design. So turbine design is a very complex and systematic job. Okay, in this case, we can see the wind turbine subsystem with the overall view of this. We have the foundation, the tower, especially the drivetrain, the gearbox. The gearbox is, as we can see, even the blade rotates very, very slow, but we can use the gearbox to transmit to the generator at a very high speed of rotation. So sometimes people ask me why we can see that the wind turbine always rotate very slow. Sorry, I have a call from my boss. I needed to pick it up. Sorry for this. Okay. Sorry for this interruption. Sorry for this interruption. It's an unpredicted call from my boss. Okay. In this case, we have also the electronic part. For the braking, for the pitch, for the power electronics, and for the cooling. The control method. So we have the drive train speed. We have a direct grid connection with a fixed control mode, and also for the power electronics for the indirect grid connection as a variable control method. So variable is a mainstream for the current control method, and also for the blade regulation. The future technology development. We have quite a different type of the turbine or the design for two different trends go higher, which means we capture the wind from like 1,000 meters higher. In this case, like we set a small jet in the air, because in the distance, in the high air, like higher than 1,000 meters, the wind speed is huge. As we can see, the wind speed is the main parameter of the power generation factor. Another thing, we go floating. We will go to this in detail in the second part of the floating type. It's very, very interesting type to see the high air turbine. The CEC, the China Energy Engineering Company, which I'm working in, is developing both floating turbine and the high air turbine. So especially for the high air turbine demonstrator project, it will be finished by the end of the year. It's the first in the world of 2,000 meters high of turbine, floating turbine. Very interesting project. If you guys are interested, we can let you to see the demo. And in this IEC standard, we have the wind turbine generator classes. We divided it into the different average wind speed, 50 years extreme wind speed as a primary parameter. So everything, people, we go to in summary, wind speed is the most important thing. Wind speed is the most important things. Okay, we are getting to the end of the first part. So do we have a Q&A part, or I go to all three parts of this presentation, we get to a general Q&A, or go after part one, we have a separated Q&A. Okay, I go to directly to the next one. Wait for it. I have I'm done using a new slide. Okay, let's go to the part two. Let's go to the general developing scenario and the case of the onshore and offshore wind industry. Currently, from IEA or the IRENA or the different energy association organization, people have the tendency to divide the onshore wind differently from the offshore wind because it have a very different characteristics. Okay. In this case, we go back. We have some fundamental of the wind power, but we have not talked about the industry. So in this case, we go back to a little bit. I will also to emphasize another thing. As you can see, the blade rotates very slowly, but as you can see internally, with the gearbox, the inside generator rotation is so quick. It's so damn quick, man. So damn quick. So if we can see outside the shaft or the blade rotates very slowly, it doesn't matter. It's so damn quickly inside. Okay. Let's go back. Let's go higher. What will be the wind power play a role in the future energy transformation scenario? So why we do this energy transformation, or what we can do, or what we will do? The reduced carbon emission, obviously. The job creation, that's the most important thing. So how can we use the solar, the wind, and any other renewable industry to make the job creation? That's the most important thing. This is we will have an industry shift in this case. Full energy access. That's the advantage of solar and wind, because we can get the access of wind and solar quite fairly inside the world. It's different like coal. If you progress, your country doesn't have the coal reserve, you don't have it. But you always have the wind, solar. The only difference is the wind speed, as we can focus on, and improved energy security, which means we can always have some inside supply of the energy. The reduced impact, great economical gain. So in this case, we have a new business model for the future. Energy related to CO2 emission, as we can see, is always the biggest CO2 emission in the world. So we want to decline this or to reduce this. We have three main method or main way to do this. Firstly, electrification of heat and transport, especially the electrification of transport. As you can see, the EV car industry is getting huger and huger. We are getting in the share market, the top three value company. The first one is Tesla. Secondly is Toyota. The third one is BYD from China. So in the next year, you can see the competition between BYD and Tesla in the Europe or in the America. In my personal understanding, the BYD have a better technology reserve and even have a better technology advantage than Tesla. Tesla is a genius of the publicity. Okay. Another one is from the renewable energy. It will provide like approximately like 40% of the CO2 reduction. So renewable energy primarily divided into solar and wind. Also, nuclear is starting to count in the renewable. And energy efficiency and other efficiency, save energy, use less energy, energy efficiency. So in this case, renewable energy and electrification delivers 75% of the emission reduction. That's a very large number. Let's go to the onshore wind. The onshore wind cumulatively installed capacity would grow more than threefold by 2030 and nearly tenfold by 2040, relatively to the level of 2018. Let's go see this number. We can see this curve, very steady. It's very steady growth tendency. It's very interesting. So now in this case, we have faith on it. That's why the industry can always put money for the R&D because we have faith. We have faith because we have a very steady growth rate. And in this case, as we can see the number, the Asia would contribute to dominate the global wind power installation by the 2050, followed by North America and Europe. So we can see that in the Europe or in the North America, they have quite small installation capacity compared with Asia. There is a phenomenon or there is a circumstance in Europe. People do not want the onshore wind power plants because they think that have a significant impact on the land field, the landscape, the view, causes the bird deaths, so something like this. But we need to notice that the onshore wind it's nearby your home, so it can directly get your personal access. It's a very convenient way to use that. Okay, another slide. And the total installed cost range and the weighted average for onshore projects has declined in many country regions. Compared with the solar, the cost decline rates of wind is quite slower than the solar. But currently, they are quietly in the same range. As we can see, the average annual investment for onshore wind deployment, also Asia, especially in China. China is like for more than half of the Asia onshore wind installation. Another next potential country is Mongolia. Mongolia has not really started its wind project, but it's in Mongolia, the wind speed is enormous. It's fabulous. It's not good for the person to live, but it's so damn good for the wind power generation. Okay, as we can see, the ongoing rates. 20 years ago, it's so small, but currently we can see that if we compare the 1 megawatt turbine with the currently installed, it's popular in China, like in the 5 megawatts. You can see the size enlargement. You can see how the manufacturing process change. You can imagine how big is the factory for manufacturing this kind of blade. And we can see the increase the harbor height and the rotor diameter, especially the rotor diameter. It needs so bigger factory for the manufacturing. For sure, it will improve the energy, yes, and reduce capital and operating cost per unit. Bigger is better. For the wind, bigger always better. You can remember that. Bigger is better. Okay, let's go to the offshore wind. The offshore wind has different industry participator from the others. We can see how it will be used. Or take an example. One of the biggest offshore wind operator is Equinor. I don't know if you guys know the Equinor. Equinor previously is a Norway state oil company. Another one is Shell. Shell also one of the biggest offshore wind investor. The Shell is also an oil company. Very interesting. So the offshore wind player, offshore wind investor is generally different from the onshore wind investor player. Why? Because offshore wind is related to the marine technology. But all the oil investor have a very solid marine technology. In this case, will facilitate the offshore wind development. They have a common technology platform as the ocean of the marine technology platform. Okay, as you can see that also a very steady rate of the growth. We can see that global cumulative offshore wind capacity would increase almost tenfold by 2030. I think a lot of people from this coast in your country have a very long coast. In this case, it's time to think how to develop the offshore wind. And even more towards to the 2050, with total offshore installation nearing 1,000 gigawatts by 2050. Asia would dominate global offshore wind power installation by 2050, followed by Europe and North America. Another, Asia always on the first rank. Offshore, offshore, onshore, offshore, onshore, offshore. Always Asia take. And currently, China is already the biggest offshore wind power plant installation country in the world. China has surpassed UK last year. Last year, UK is the biggest country of the installed offshore wind. But this year, China has become the biggest country. And the trend has not been stopped. The growth is continuous, especially as you can see. We look at the country plans for offshore wind power development. China has the most ambitious, and the Chinese Taipei. The German has a very special coast for the offshore wind resources. India, Japan, Korea, New Zealand, the UK, and the United States. United States is a very interesting country. they have their national energy policy changed every 4 years with the change of their president. Every time their president changed, their energy policy changed. So their when the Trump comes to the place, the oil comes back. And when the Biden and administration comes to their place, the wind, the solar comes back. So no one can ever predict the future of the wind in US because we don't know which party will be dominate their politics, especially with the current Biden administration. We will never know who will be the president of the United States in for 2 years, in 2 years. Never knows. If Trump comes back, the prediction of installed wind of US will decline significantly. So no one can predict the US currently. Okay. The leverage cost of the offshore wind is already competitive in certain European market, Germany, UK. Everyone wants the offshore wind to be a zero subsidy. China, from this year, the offshore wind is in the zero subsidy in certain province. So in this case, on the competitiveness in other European markets. So it is expected to competitive in other markets across the world by 2030. It's a very slow prediction. I think it will be 2024. As we can see, the cost reduction is very quick, Okay, we can see the average annual investment for offshore wind deployment. With the contribution of China, the Asia will depass Europe very quickly, and in the future. Why we can see that in the Europe, the number is we didn't see a lot of improvement in Europe of this. Why? This is the hesitation of the UN, of the EU. Because the energy controlled by UN is very limited. Expected from the offshore wind, they have Europe have very limited solar. They close the coal. They don't have the natural gas. So Europe is in confusion. They have changed their goals last month. Due to the war between Ukraine and Russia, the Europe has pushed the Repowering Europe initiative last month. They have published. So they will invest 10 times than ever for their offshore wind power. So this is the number of last year. So in this year, we can see that the war between Russia and Ukraine has changed so many things. The politics, the economics, the energy geopolitics map, it changed so many things. Okay. There is still a lot of R&D activity in the offshore wind power. We can get some high potential impact technology in approximate order of priority. High, medium, low, and it's very typical. Future generation turbine, reducing the cost of energy for sure. For sure. Grid, increasing grid integration, moderate. That's for sure. The bigger turbine can generate more power, but it cannot resolve the problem of the integration. Opening new markets, moderate, no new market. Always the same player, like the Vestas, the Siemens. Decarbonizing environment impact, moderate. We cannot see a bigger turbine contribute to the environment. Improving health and safety, that's for sure. Why? In this case, for the same power output, we use less turbine. So in this case, we install less turbine. So we reduce the risk of the health and safety. Floating foundation. Repowering of sites. We can see that the floating high, opening new markets, which means floating. So the foundation technology opening new markets. Decarbonizing environment package. Why? It's floating foundation. So during the construction of the foundation, the environmental impact will be significantly reduced. Repowering of sites, integrated turbine and the foundation is installed. It's very interesting. We combine the foundation and the turbine together. HVDC infrastructure, because we're getting very far away from the land. And the DC power takeoff and array cable. As you can see, it's moderate and low, and site layout optimization. This is quite mature technology. We cannot get quite a new output from this. So in this case, we can see that the most relevant development we need to contribute in this category development. Turbine support structure. Floating is an innovation of the support structure. Electrical interconnection, HVDC, is a new type of electrical interconnection, installation, and operation maintenance service. So we can see that in this. Different things will be done in different period. The first boom offshore wind is already bigger than the onshore wind. And we can see always have a bigger offshore wind than the onshore wind because we have a larger or the better wind speed offshore. So as you can see, the average size of the offshore wind turbine grew by a factor of 3.4 in less than 2 decades. That's a huge improvement, huge growth. As you can see, the 15 to 20 megawatts will be the standard in the next 2 years. The GE has already have his 50 megawatts prototype in test. It will be in operation maybe next year. Things go so fast. And the floating foundation. So technology development in wind turbine foundation, one of the key factors enabling the accelerated deployment of offshore wind. Let's say, focus on this one, permitting access to better wind resources, which means we can go to a even more depth of the seas condition. Okay, this is estimated floating wind potential in China for different depths and the average wind power density. As you can see, the depth and the wind power. So in this case, we're getting a floating foundation. The foundation is more expensive, but it can be compensated from a better wind output. So it's very interesting to calculate that. The floating foundation is the primary tendency in the future. Okay, as you can see, the offshore coastal wind power, potential of floating offshore wind power in China. A lot of demonstrated project of all floating project is undergoing in China. One project in operation, one project in construction. It's all in the Guangdong province. Especially we needed to know the red area. The best offshore wind resources of China is located between the Fujian and the Taiwan province. The tunnel, we can see the sea tunnel can increase the wind speed. This is the three primary type of the floating foundation: the tension leg platform, spar submersible, and the spar buoy. All of the three types of floating foundation is driven or is taken from the oil industry, for the oil extraction industry of the sea. The next one is integrate rising shear wind power generation. So we can see the different wind penetration. This is 1916, 1930, 1950. We have different wind penetration, onshore, offshore. Higher share of wind power would be integrated in various G20 countries. So as we firstly mentioned in the previous slide, if we get a 5% of penetration of wind, it doesn't matter. The integration is easy. But if we get a 30%, the variable of the renewable, of the wind, the variable of the solar will become a very big problem in this case. We need to resolve the integration of the wind. Okay, so in this case, we can see that additional investments are required in grids, especially the generation adequacy and some flexibility measures, the energy storage across the entire electricity system to increase the rising share of reliable renewable resources. As you can see, we need several measures to adapt to these flexibility measures. The transmission grid, we need to update the transmission grid. We need to update the distribution grid. When the generation resource is variable, so we need this smart grid to be variable. The consumer of the electricity to be variable also. So we need to update a lot of things, the whole grid. And we also needed to energy storage to compensate the variable, especially the solar. We don't have the solar in the night, but we come back from the work. We need the electricity and the smart meter and the dispatchable capacity. So when we have a higher wind power penetration, this power system flexibility is crucial, is fundamental. As you can see, we have several enablers. The generation, the power system flexibility, from generation, distribution, storage, and demand side management. The demand side management become more and more important, which means as a building, we are in the building as a consumer, building as a consumer can also use in the demand side management. We are the demander of the energy. When the resources is variable, we need to variable. In this case, the grid give you indication. Reduce the air conditioner power usage. You need to have the capacity to follow the indication of the grid. You can reduce the air conditioner very quickly. And the sector coupling, also a very important measure of it. The heat, the gas, and the electrical vehicle. So sometimes the electrical vehicle can also provide electricity back to the grid. So we can see the innovation and the dimension, the enabling technology. It's very important. Without all these measures, the wind power cannot be developed to the scale as mentioned. No way of that. So the utility scale battery as energy storage measures behind the meter battery, which means the battery or the energy storage of the generation side. So which means the battery is integrated in the wind or in the turbine even. And the electrical vehicle smart charging, which means we want it to charge depends on the need of the grid and the renewable power to heat. We use the heater to generate the heat wired directly from the power from the wind or the solar, renewable power to hydrogen, Internet of Things, and artificial intelligence and big data. We can have a prediction. With the AI and the big data, we have the prediction to know what will be the energy scenario tomorrow. The blockchain for the trade and a renewable mini grid, which means it's a solo one. There is no grid in support. It's a solo one, a super grid. Like in China, we try a super grid to transmit the renewable from one place away, from a place 2,000 kilometers away to another place. And the flexibility in the conventional power plant, which means in this case, coal-fired or gas-fired power plants will follow the renewable. The business model, we need the peer-to-peer electricity trading, the energy as a service, and the community ownership, and also for the market design and the system operation. When the rise of the wind, with the rise of the solar, a lot of things will be changed. Okay, we can also to do something about this. The onshore and offshore wind industry have for the job creation. That's the beneficial side. As we can see, it can create more and more job for this. This is another aspect of this, the materials required. For example, we'll take an example for the 50 megawatt onshore wind power plant and all the offshore plants. As we can see, the concrete, steel and iron, the polymer materials, many for the blade, the fiber glasses for the blade. Because fiberglass is very tough, but very lower weighted. Aluminum and alloys, copper and alloys, electronics and electric, and oil and coolant. This is also for the offshore wind power plant. In this case, it's similar, but it has a very complex foundation, because in the offshore, the foundation is very complex. So we have a more foundation structure than the onshore plant. Now this is a value chain. That's why a lot of government, especially the local government, want to introduce, want to build, or want the turbine supplier to build the factory in their neighborhood, because it will quite beneficial for the local business, local economy, to build a local value chain. Because a lot of sub-supplier of this turbine supplier will come around to its factory. So it will have very bad the job creation. So we need to introduce this turbine supplier to the local. So good for the economy. Yet still some existing barriers in the wind industry sector. We have some technology barrier, grid connection, and the integration challenge. We have already mentioned that. Lack of supporting infrastructure. Sometimes there are even no grid substation in the neighborhood. Concerns about technology maturity and the performance. That's very popular in the offshore wind. And harsh offshore natural condition. Yeah, that's for sure. We have typhoon, a lot of things. Economics and market barriers. High initial cost of capital and the long payback period. Generally, the payback period is at least 15 years. So we need to be patient on it, very patient, and limited the financing channels. But in China, the bank is very supportive with this kind of situation. I don't know what's the bank's attitude in other countries, but in China, especially the national bank is very supportive in this way. And the immature offshore supply chain. That's for sure, because offshore has developed with very limited time. The supply chain is not mature. And the evolving policy with the impact of remuneration. This is changing. It's not very serious. And the carbon emission and the local air pollutant are not priced or fully priced. This is not a major parameter. Compared with solar manufacturing, the turbine or the wind manufacturing emits less CO2. All the manufacturing will emit CO2. But compared with solar, the wind emits less CO2. And the regulatory and policy social barrier. Complex, outdated regulatory framework. That exists in a lot of countries. Even in Europe, sometimes there are regulatory cannot very rapidly support the planned construction. Insufficient financial policy support. For example, the tax reduction. Lack of relevant standards and quality control measures. The IEC, IEEE, and ISO has published quite a lot of onshore regulation, but for the offshore, this is for real. Lack of skilled professional experience, especially for the offshore. It's a marine technology. It's a marine project. So in quite a lot of countries, marine technology, a skilled person is missing. A lack of long-term stable policy targets and well-coordinated policy mix. For Europe, they have a revolving initiative that's okay, but I know for that in the Southeast or the Southeast Asia country, this is a challenge. Transport of wind turbine components, that's very for true. As you can see, the blades more than 100 meters. So the transportation is not easy. It's not easy. And environmental barriers, we will ignore that. Okay, we are getting to the end of the second part. So, any questions? Or any questions? So we are the moderator of the meeting or the coordinator of the meeting. So I go directly to the third part. Is that okay? Okay. Okay, I go to the third part. Okay, wait a minute. I will share a new documentation. Sorry. Okay. Everyone can see this clearly?
Yes, Mr. Wang, we see it very clearly. Please
Okay.
go ahead.
Okay, thank you. Oh, we will focus on the technology innovation because this is what we can do to get the innovation advantage. The secret of the China development is to the technology innovation. We have a data of the IEA organization, the International Energy Agency. In the top 10 turbine supplier of the wind, there have been 6 companies from China. There is only 3 companies from China 5 years ago. Up to now, there have been 6 Chinese companies. So we needed to focus on the technology innovation. We have the tendency of this. We can see that the next generation wind turbine. So we conducting earlier stage research on the promising rotor configuration, turbine architecture, and the manufacturing approach. And we can see that the floating offshore wind system focus on the control, reliability, modeling, and simulation. This is one missing point, like a validation and the certification. That's why we go back to the last page of the second part, the missing standard of offshore, because we need also a standard of the validation and the certification. Certification of the offshore part components is very hard because we cannot to certify it really on the offshore. We can only simulate the condition, especially the wind speed, the humidity of the offshore condition. It's harder on the onshore to do it onshorely, but we cannot really to certify it in the offshore condition. So it will increase the cost of the certification. And that is the big challenge. And the plant level control. The reducing the load of the wind turbine components while capturing more wind energy and giving it to electricity. That's very important things to do. So we can even update the existing power plant. And driven train technology, operation, and maintenance. Developing advanced driving trains and the technology to increase performance, the torque density. That is the mechanical technology will play a more important roles in the future. Okay, the next wind turbine. The areas of the expertise, which means some all the kind of the science, technology guys to do in the future. Aerodynamics, aeroelasticity, computational fluid dynamics, and high performance computing. This is from US documentation. That's what we needed to do. As we can see in the US, the current project. In China, we always to see what the US do or what the US are doing. So the challenge, the approach, and the impact. Another one is the floating offshore wind system. As we can see, we have mentioned these 3 types of different foundation types, 3 types. We mentioned in the last slide. Okay, the challenge and the requirement is also the industrial need. What we need in the future, we need to building wind plants in the water depths greater than the 60 meters offers a tremendous opportunity for wind deployment, and including almost the entire west coast of the United States. In China, the entire east coast of China. And the deep offshore opportunity requires floating solution that stretch the capability of system design and optimization. NERIA, the National Renewable Energy Library, offshore wind turbine research, focus on the long-term needs. We have done very deep analysis of ARENA doing. We compare what Japanese are doing, European are doing, and what the Americans are doing. We have a very common approach to the floating offshore. We can see the current project. We have been doing the very similar thing. We have in China also we have the indoor simulation of the floating foundation. We have doing basically the same thing, but we getting the bigger prototype. As you can see, the pin joint. We have also already improved version of this type. And there is an artificial wave starter. As you can see, we cause the wave indoor and to simulate how the floating foundation react under different circumstances, different situations. Okay, also we can see that in the floating offshore wind, the US has added different new components to giving it a better balancing capability to adapt it to a better usage. Okay, the next one is the plant level control. Especially, we can see that advanced wind turbine controls can enable annually energy production and reduce losses by more than 20%. The calculation or the number from our plant, our currently in operation plant feedback is like 25% even. So we can have a different technology. For example, with the application of the plant level control algorithm, a different regulation system for a 300 megawatt wind power plant, the expected outcome would generate one additional $1 million per year. And that's very good beneficial, very good feedback. Drivetrain technology, operations, and maintenance. This will give a very common platform for the existing plants to reduce their maintenance time, improve their maintenance quality. In this case, they will have a better feedback of the generation time and the generation rates. And in this case, we have already compared what the Americans doing. I think we're doing this better in China for this reliability and the gearbox. The primary gearbox manufacturer is all of the main gearbox manufacturer is from Europe. All the top 3 gearbox supplier is in the Europe. So neither China, neither US have a very good gearbox supplier. All these good suppliers are located in Europe, in Germany, in Denmark. Okay, I think I have already made this presentation quite clearly. I have some additional slides about the plan and the perspective of Asia wind power development, but I don't think we need to expand the range of this presentation too large. I hope we can have some more question and answer time to know what you guys interested. What are your interesting points? No questions?
Okay, thank you, Mr. Wang, for your informative and enlightening presentation. And any one of you have any question or any comments on this session? If you have any question, please feel free to type in our chat box. And I think Mr. Wang will be very happy to answer all of your questions.
So the coordinator of the meeting asked me to reserve some time for the exchange. So if no more questions, I can also go for the Asian wind power development schemes.
Yes, Mr. Wang, I think you can continue with this part, and
Okay.
I think it will be
problem.
very useful and informative to all of our participants.
Okay, no problem. Okay, so now I will give you some presentation of the Asian installed capacity of the wind power. I think in the 2025, under the base case, all the renewable energies is around, I think, 21 of the total installed capacity. But under the APEC renewable target, it have 10% more for this. So under this base case, there is some new planning scheme, new planning system has been initiated. As you can see, the base case and the target are different. And we can see the Asian renewable resources potential. It's got a very good resources. We have the solar resources, the wind resources. It have quite good growth capacity factors. And quite a lot of different countries have already done their wind map, the wind resource identification map. It's very useful in this case. It's very useful. We can from Indonesia, Thailand, the accuracy is acceptable. I have been in some country for this evaluation process to evaluate the accuracy of the wind map, especially the wind allocation resources map. I think the accuracy is acceptable. And to the Asian wind development, the current state, as we can see that. In different country have a different installed capacity, power generation. We can see that Vietnam, Thailand, Singapore, Philippines. Singapore cannot; it's too small for. But Singapore is currently estimated their offshore wind plant. Malaysia, Laos, Indonesia, and Cambodia. For the last 2 years, 1920, Asia region has recorded the installation of 4.4 gigawatts of wind energy. Compared to the speed in China or in Europe, it's quite slow. It's quite slow. We expected much quicker installations speed in the future. So in this case, we can see that Asian country, in the Asian development, there is a deployment target, the Philippines. The Philippines has set the goals of achieving the total installed capacity of wind power of 2,300 megawatts by 2030. So it's 2.3 gigawatts. I think Philippines could increase the number by 10 times. Because in Philippines, the offshore wind power resources is so good. And Thailand is 3 gigawatts. And Vietnam is 6 gigawatts. So all of this has not taken into consideration of the offshore wind. Offshore wind. So if we can take into consideration of the offshore wind, the number will be bigger. In this case, we can see that we estimate the offshore wind differently, not in the same category, in the onshore and the offshore. Because not every Asian country have a seaside, so some country only have the onshore wind installation capability. So in this kind of Vietnam and the Philippines will conducted the offshore project. For example, Philippines has conducting the feasibility study and the offshore wind development roadmap. I have been the Asia Development Bank energy expert. I've been in Philippines for several times before the COVID-19. So I think the Philippine condition is quite good for the offshore wind development. Okay, and we have the formulated related goals and the policies. Policies is very important, especially the feed-in tariff, the FIT, the tax preference, and the financial support. So in China, some organization in China has the suggestion for the wind development in Asia. We have published this documentation. So we have some important suggestion to accelerate the deployment of wind energy in Asia. First, set a clear goal on the wind and adopt incentive policy. So a clear goal is very important. So in China, the central government set a very clear goal of the solar wind development. The national company, firstly, take the responsibility to fulfill the national needs, and all the private, the foreign country also will take their initiative to do this job. So a clear goal is fundamental and very important in this case. Secondly, the layout optimization to promote the development of wind project in orderly manner. So first thing first. So better condition first. So we need to have a very good plan in this case. Sorry, I got another call, sorry. Look. Oh.
Okay, dear friends, sorry for the interruption, and we just wait for 1 or 2 minutes, and we will continue later.
Okay, sorry for the second interruption. I'm feeling deeply sorry for that. Okay, we go that way. The layout optimization. So we need to, for the site selection, the location of the wind power plant is crucial for the cost estimation. So we need to have a development scheme. Establishment of the Asian wind power technical standard adopting from local conditions. It's also very interesting thing. We have met in the Asian country. There is a European supplier. There is an American supplier. There is a Chinese supplier. There is a Japanese supplier. So they always, so the European supplier follows the EN code, which means the European norm. So the American supplier follows the ASME code, ASME, and the US code. So the Chinese has our national code, but our also conform to the UN and US code. The Japanese has their GRT code. So in this case, one thing is very spire items. How could you get a very common spire items? So in this case, for the Asian country, I think all these countries can be united to get a common local technical standard. All these countries share a same one. to reduce the spare item difference. The first one, so the exploring the innovation of the financing models. So because for the local bank financing capability is quite low. So in this case, could we open this to the foreign bank? Because the financing capability of the ADB or the AIIB is also limited. So we need to have a more financial resources to get inside this market. 5, the win-win international cooperation on wind power. For example, for Philippines, for the Vietnam, for any other country, you can simulate the Chinese way 20 years ago. So we exchange our market with the technology. I can give the market to you, but you need to manufacture your blade, your turbine in my country, in my city. So we call this exchange market with technology, or always manufacturing. And in this case, it's a win-win model. Win-win model. Okay, I think I have finished my presentation today. All the questions are welcome. If you guys have some interesting point, I'd like to be shared with that. Okay.
Okay, thank you, Mr. Wang, for your presentation. So, any questions? Or you have any comments on this presentation? Please do not hesitate to type your questions in our chat box. So in this session, Mr. Wang gave us a very detailed introduction of the development status and technical application of the wind power, the onshore, offshore wind, together with the latest data, policies, and some case studies. And at the end of the presentation, he also shared with us with a plan and a prospect of ASEAN wind power development. And I think all of this information would be very useful for our participants in this field. So if there is any question or you want to share your opinions, please feel free to type in our chat box. Okay, Ms. Wang, I think our participants are all from all the officials and experts from are all engaged in the clean energy, electrification, and other related fields from the government or the enterprises. I think they are quite interested in this topic, and I think if they do not have further questions now, maybe if they have some further questions afterwards, I think we will gather all the questions and we will contact you, or they can directly contact you via the email in the future.
No problem. All the kind of exchange will be welcome.
Okay, so thank you so much for today. And I think we will call it for today. And goodbye and see you tomorrow. Bye-bye.
Okay, thank you. Bye.
Thank you.